Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but you know, I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
Hello, everybody. I hope that you can all hear me.
Welcome to another episode of Ask Us Anything About Electrochemistry. I'm your host, Dr. Alex Paroff. My colleague, Dr. Neil Spinner, is out right now, and I'm just dealing with some of the technical stuff that he usually is able to fix. So, just trying to make sure I don't have feedback. So, if you are listening right now, please type something into the chat. Otherwise, I will try to kind of manually operate this to make sure that everything is running smoothly. Anyway, welcome to another episode of Ask Us Anything About Electrochemistry. Again, my name is Alex. My host, Dr. Neil Spinner, is out right now. We're also doing a live stream on a different day. It's Thursday, and it's not Friday, the usual day. Just because the summertime for both Neil and I is very busy. We have lots and lots of things going on. So so Barry says a Thursday live stream. Yes. Because tomorrow I'll be busy, Neil is out, and then the following week I'm out. Neil might be able to do something, but I am trying to get as many of these episodes out as I can to answer questions and just keep the live stream going. Also, if there are people who normally can't attend the Friday session, this Thursday one's just a shot, just trying it. Also, before I begin, I'd like to thank anybody who visited me at the Pine Research booth at the ECS meeting in San Francisco. That's right, not San Diego, San Francisco last week. Thank you for stopping by. I had a lot of great pictures with people and people who watch the YouTube channel as well as the live stream. And it's always great to meet fans in real life. My hope is that I am able to make more videos in the future for you guys. So to talk to you a little bit about how the live stream is, if this is the first time you're watching it, or if you're watching this live stream after the live stream has been done, we'll try to go through as many questions as possible about electrochemistry. And really, we have found that there are lots and lots of questions about electrochemistry, and sometimes either a webinar or a YouTube comment or just answering a question in the middle of a webinar or phone conversation might not be the best way to answer that question. And so we try to use YouTube and a lot of other tools to teach some electrochemistry based on the questions that you have. We have found that questions that are super general might be hard to answer. Generally speaking, if it's a broad question like what is cyclic voltammetry, how does it work, how does EIS work, it might be too broad of a subject, and it may be more appropriate for, say, one of our webinars or even our YouTube videos to help kind of answer that question. Also, if something is too technical, if it's too detailed, I might not be able to answer a very specific detailed question that has to do with the activation energy of a specific reaction. But questions that are kind of in the middle, clarification about complicated electrochemical concepts, is something that we can probably try to do. Also, a heads up is Neil is really the expert when it comes to EIS and batteries in particular, and we do get a lot of questions about that. So if I'm unable to answer a question, it may be the following live stream that I may ask Neil for some clarification about some things. But aside from that, I'm hoping to go for about 2 hours for this live stream. If you're watching the live stream after the live stream is done, then I'll try to have timestamps in the description below, and you can catch up. Apologies in advance if I mispronounce any names, and I think that's all the boilerplate stuff. So let's begin. Also, let me know if you can't hear me or if there's some technical feedback or something like that, as I don't have, whenever Neil's on his own or whether I'm on my own, the live stream, the pacing, we always need a little bit of help from the audience to make sure we're good. So we have a question here from Manoj. Let's go through it. So step by step. Manoj, in LSV technique, I am getting a peak in between from 0 to 0.2, and after that, the graph starts to increase in the linear manner.
what might be the reason for it might be due to the cell setup, or due to the electrolyte problem, or due to my working electrode. I am in photoelectrochemical water splitting application using the thin films coating in, I think it's FTO, or indium, or maybe it's in or indium. I'm not so sure. Indium substrate. Thanks in advance. Okay, so specifically the question, Manoj, that you're talking about is getting a peak in between. So this is LSV, so linear sweep voltammetry. And you're getting a peak between 0 to 0.2, assuming that's in volts. And after that, the graph starts to increase in a linear manner. What might be the reason for this setup? So, to a degree, I kind of want to know a little bit more about what this looks like. So let me at least share my screen, and I'm gonna hide this question for now. Oh, these windows are not up. So let me do that quickly. All right, so I'm here, and let me just make sure that everything is good. I'm going to hide this, and Manoj, please give me some comments so I can, if I'm getting this right. So what you have described, Manoj, to my understanding, and correct me if I'm wrong. So this is LSV. You got voltage and you have current on the y-axis. You're scanning, you see a peak, and then, maybe this is 0, and this is 0.2. I'm assuming it's volts. And then what you've described, the way you've mentioned it, is you said that there is the graph starts to increase in the linear manner. The linear manner after this. So let's take another look. So the linear manner, if it's a linear, it's something. It's usually something. When I think about linear, I think about something like this. It's just going up, like so. I've had other things, just to let you know. I've seen other things where it's like it starts to exponentially increase. But what you've mentioned is a linear manner, which I've seen before. I've seen sometimes where it's just linear, but I've also seen this kind of huge exponential increase. And you want to know what this linear increase is for. So my guess, not knowing everything about your system, of course, I want to say this has a bit to do with the potential window of your particular system, say the electrolyte. And I do think it might be due a little bit more towards possible electrolyte degradation, or doing something to the electrolyte. Let me see if, let's see. Okay, so Manoj clarifies. He says exactly the same graph. Yes. Okay. So for further application, thin film. All right. So you do have a thin film. That's an interesting thing. So I want to make a note that you do have a thin film. This is a thin film study. And it's, let's see, it's a thin film. And you're getting this. So one thing that you might want to ask is, are you getting delamination? Are you getting some kind of, could the film be coming off the surface? When I have a blank, what I've observed in the past, and the only time I've seen stuff like this before, like whenever I've seen stuff like this before, it's usually on its way to going like this. It's on its way to becoming exponential. This usually hits me as some kind of resistive type of experience. I think electrolyte usually plays a role in this. Usually if it starts to exponentially increase, it's usually like oxygen or hydrogen evolution. But to me, this hits me as something a little bit different. It's not the rapid onset of hydrogen evolution or oxygen evolution. And I think in this case, because you're sweeping positively, you're generating oxygen in a water splitting type of system. So I would be curious to know Manoj, one thing that you can do is if you keep sweeping, if you keep going further, do you eventually get, and this is something where you may have to test with something that you're okay with potentially destroying because you are going to very high positive potentials. Do you eventually get this kind of exponential increase? I suspect because it is 0.2 volts, not 100% sure about the reference electrode or roughly what potential it is. I do think there may be there's some kind of resistance, and I do feel like the thin film can cause some resistance at higher potentials. But there's a part of me that just feels like it has to do with the electrolyte. I can't put my finger on it. I don't know exactly why, but I don't think that it's necessarily gas evolution, because you usually see an exponential increase as opposed to a linear increase. It hits me as something resistive, something that's resistive. So it is possible that maybe you're generating, because some current, I would be curious also if you do reverse sweeps, like a cyclic voltammogram instead of LSV, whether this continues to grow. Because does this disappear when you do the reverse sweep? I kind of think that there may be something on your surface on top of the thin film. It's a guess, but that's kind of my take on it. Let's see. So exactly the same graph till one level. I've got the same. Till 1 volt. I got the same graph. Okay, so 1 volt is still around the level of you're getting close to oxygen evolution depending on your thin film. And you did mention that the film didn't peel off. There's a part of me that suspects it has something to do with the electrolyte. That's just my guess, Manoj. Without any other knowledge, I would be curious if you tried to do this without a thin film, what would you get? So hopefully, Manoj, that at least gives you something to think about. I'd have to think about it a little bit more of what it could be, but sometimes it is the electrolyte and not the. It could be the working. I feel like it's either the working electrode or the electrolyte itself, because I don't think it's hydrogen or oxygen. I don't think it's oxygen evolution. That's just an intuition. All right, Zaki, let me see. Zaki asks, why do we use a bridge tube for reference electrode in electrochemical cells, especially when the solution inside the tube is the same as the electrolyte? That's a very good question. So sometimes the reference electrode fill solution inside that tube is not going to be the same as the electrolyte. If it is the same as the electrolyte, then perhaps you don't actually need to have a that kind of tube. You could actually just have a regular wire. But I would clarify that it's not just the electrolyte, but it's also the same concentration of electrolyte. A lot of these reference electrodes consist of a saturated solution. So silver chloride usually has a saturated 4 molar potassium chloride solution inside of it. A lot of people don't do electrochemistry at 4 molar. But 4 molar keeps the concentration of chloride ion the same. So I hope that kind of answers your question a little bit. Why is the reference electrode in this tube? And usually it's inside of this tube. And actually, I will draw this so that you can kind of visually see. So let me draw things, because I think drawing things helps give everybody a visual clue of how this is. So just so that people are aware, reference electrode construction looks a little bit like this. And let me just double check to make sure that this is sharing, because sometimes it doesn't share. Okay. You tend to have some kind of wire. Maybe there's a salt around it. You can have mercury. You can have mercury oxide. So you'd have a mercury oxide salt, metal plus a non-metal, so salt. And there is some kind of fill solution inside of it, and there's a frit. inside. So this is the typical construction of a reference electrode. So the goal of the reference electrode is to maintain a stable potential, and the potential is dependent on the Nernst equation. Won't get into that too much, but this is the Nernst equation. Actually, I guess I will get into it. So if I go back here, and actually I'll use the lasso tool, I can copy this guy and put him here. All right. So the Nernst equation governs the potential based on the E naught minus RT over NF natural log of the activity of the reduced and oxidized species. For certain reference electrodes, you may have a kind of a quasi Nernstian system, because some of these will have a activity of 1. So you actually, the potential is only based on the concentration of one thing, such as silver chloride. So chloride ion is usually the thing that governs or moves the concentration or the potential, sorry, of your reference electrode. So most of the time, the reference electrode solution concentration is not the same as your electrolyte solution for your electrochemical cell. And the reference electrode is just supposed to be stable because this concentration needs to stay the same. If it starts to change, your potential starts to change, which is what you're measuring your working electrode with respect to. So hopefully that helps you. And let me just see whether or not you have like a follow-up. It doesn't look like you do, but that's the reason. That's the reason why we use this kind of bridge tube design for a reference electrode. So hopefully that makes sense. All right, moving on. We have a couple questions. Very good. All right, so FCB. We all know that Nernst equation is applicable when the equilibrium is established and current is 0. But for galvanic cell, we get current and concentration of species by applying Nernst. That's a great question. So in that case, in that very specific case, I would say the Nernst equation doesn't apply, because just as what you said, it applies for an equilibrium situation and for some galvanic cells. And maybe I'm kind of misspeaking here, but when current is flowing, you have a transient system. You have kinetics possibly happening, and the system is not at equilibrium. One thing that I want to point out with this is that in a technique like cyclic voltammetry, we say that when we get a cyclic voltammogram, and let me just show a simple cyclic voltammogram from our software. So this is our Aftermath software. I'm just going to simulate a cyclic voltammogram very quickly for you to see, and then I'll just simulate it, and then we can look and talk about this. One thing that we commonly use or get with cyclic voltammetry, and let me actually just hide the question so it's a little bit easier for people to see. But one thing that we usually say is, oh, we get thermodynamic information from cyclic voltammetry. Well, there's current flowing. How do we get, there's current flowing when we do cyclic voltammetry. It's a transient technique. How are we able to get a good E naught value from the cyclic voltammetry? How is the Nernst equation applied to a cyclic voltammogram? How do we know that the concentration profile here follows Nernstian behavior, like we know that. But that is partially because the kinetics of the electron transfer are very fast. The current is changing. The concentration at the surface of your electrochemistry experiment is changing. But if the electron transfer is super fast, and in this case it is, I got a heterogeneous rate constant of 10 centimeters per second, then you can say that equilibrium is established very quickly. So if your system has a current and the equilibrium is established quickly, then the Nernst equation and Nernstian behavior would apply. That's the way I at least see it. Of course, if the kinetics are slow, then your Nernstian behavior is not going to work out quite as well. So that is that's kind of my answer, my my description when doing it. If you're able to establish equilibrium quickly, then the Nernst equation applies. But it is something that only applies for equilibrium, an equilibrium system. All right, I think I just want to check. I thought it was lagging for a little bit. That may still be the case, but hopefully not. All right, let me go through this. I think a lot of great questions coming in. All right, Sudipta, I hope I got that right, is asking, can you explain how the rate of the reaction can be deduced for homogeneous water oxidation electrocatalyst by foot of the wave analysis? Please elaborate. So I have heard of foot of the wave analysis, but the truth is I don't know enough about it. And I know that my colleague Jillian Dempsey uses foot of the wave analysis to actually deduce rates of reactions for homogeneous electrocatalysts. So unfortunately, Sudipta, it would be a mistake for me to actually show you how foot of the wave analysis actually works. In principle, I will at least describe this. The foot of the wave of a CV, and I'll at least let me share this again, so hopefully you can see this. So when they're talking about foot of the wave, they are talking about these areas here, like or actually, I'm doing a reduction. So this lower part of the voltammogram, nothing is happening until you start to reduce, in this case, A to B. This area here is, in a way, a mixed kinetic, mixed diffusion, mass transport limited region. So it's in this region that you're really starting to get some kinetic information, because diffusion is, your current at this point is not diffusion limited. And so it is because your current is not diffusion limited and you start to observe current, you are starting to see the current move. You can extrapolate some useful kinetics and get rate constants. I personally would say using something like electrochemical simulation software might be another or a better way for getting a heterogeneous rate constant, or even TAFL analysis with like a rotating disk. But at the end of the day, I don't know enough about foot of the wave analysis. I would need to learn more about it to actually elaborate further. So I'm sorry, Sudipta. Okay. All right, so moving on. BGMI Shorts asks, I am new to electrochemistry. What is Faradaic, non-Faradaic region in CV? How it is related to potential window? That's a great question. That's a great question. So I'm going to draw this for this one here. So let's go back to the drawing board. I'm going to delete this guy. So let's talk a little bit about Faradaic, non-Faradaic. And we have a CV, we have our voltage, we have our current. And then I'm going to draw a voltammogram. We have a nice peak. And then we have maybe some kind of oxidation process going on there. As we go to higher potentials, we have this reduction, and then we have here, and then this kind of goes down. Let's just call it that. Let's just say this is our CV. So to get to your question first, as you're new to electric, what is Faradaic and non-Faradaic region? So the Faradaic region, in a way, is actually this kind of region here, where there's an electron transfer process occurring. So Faradaic means, really, it means current associated with an electron transfer, an oxidation reaction or a reduction reaction. Technically, this area here is also Faradaic. This area here is also Faradaic. There are electrons transferring. So let me make another window to kind of describe this a little bit better. So if you have this is the way I kind of think about Faradaic and non-Faradaic in an even more fundamental aspect. So if this is my electrode surface, I got molecules and ions kind of floating, diffusing around in solution. When these ions move towards the electrode surface and they balance, say, negative charge, so if this is positive and it's moving, when this negative charge moves to counterbalance the positive charge, current is measured. Your potentiostat measures current. The moment the ions are moving, or electrons or charge, more accurately, is moving in your metal, there is current. It could be a small amount of current, but there is current. But there's no electron transfer. This is a non-faradaic current. So current flows because these charges are moving, but there's no electron transfer. The moment you have something like another molecule, let's just say this one. If this gains an electron, if there's an electron that literally moved from the metal to the molecule, or if you have an oxidation process and it's from the molecule to the metal, that is a faradaic process. So electron transfer occurred. So even in this region over here, electrons were transferred. This may be oxygen evolution right now, but electrons are being transferred. It's a faradaic process. So this area where there's normal peaks, reversible cyclic voltammograms, and this area where you have, say, hydrogen evolution, those are all faradaic processes. Now, current in these other regions, and I'll just use a red pen for now, so like this area here and this area here, those are the kind of non-faradaic processes. Now, I should mention there's a little bit of a caveat. Faradaic processes are still occurring here. So this current is decreasing, but there is still current associated with a faradaic process. And for that matter, there is still non-faradaic current in this region as well. So only in the case, actually, this region here is really the only region where I would say it's a true non-faradaic. There's no electron transfer at all. I mean, you only get electron transfer here and here that's associated with, say, gas evolution. But this area is truly non-faradaic if I'm looking at this as like an oxidation reaction here. Because even in these potentials, you're still oxidizing your species. They're still faradaic. So there's faradaic and non-faradaic in this region, but I would say there's more truly non-faradaic in this region. I hope that's kind of helpful, but that is a description, because I do want to get to all the questions that are coming in. That is a good kind of description, I would say, of the difference between faradaic and non-faradaic. I guess the last question you asked is related to the potential window. So the potential window is just, it's the edges of your cyclic voltammogram. And it's usually a point where you're breaking up a part of your system. So in hydrogen evolution or in oxygen evolution, sometimes you can't see anything past it. So even if there was a electrochemical process occurring at that potential, you wouldn't be able to observe it because it's convoluted by the hydrogen evolution or oxygen evolution. So whether a reaction is faradaic or non-faradaic does not necessarily directly relate to the potential window. I hope that was helpful. Let me know, of course, for anybody, if you need further clarification, please let me know. But it does look like we're getting quite a few questions, so I'm going to hopefully try to get through these reasonably quickly. Let's see. Reaction. This is from, looks like OO. So reaction A goes to B plus an electron, an oxidation reaction. What difference does the current voltage graph show when it is reversible and irreversible? What happens to the graph if the concentration of A is 10 times greater than that of B? This is a very, very good question. Great question. And this is actually a question that you can answer on your own if you decide to use our software Aftermath Live. I'll show you how to do this, but let me show you that our software, and I will I will go to our software. Our software has simulation software built into it. So I'm going to minimize your question for now, just so that I have it. So I'm going to just hide this. So this is again A. So let's do this reaction. So we have A plus an electron goes to B. So that's this. I just switched it to oxidation, right? So A plus an electron goes to B. And you want to know, let's go back, what difference does the current voltage graph show when it's reversible or irreversible? So let's actually do that. This is a reversible reaction. And in this case, you see a reversible CV. So I'll simulate it again. So actually, let me change the voltammogram because we started here where I'm oxidizing all of my A to B. So what I'm going to do, I'm actually going to switch this. I'm going to start at minus 1000. I'm going to go to 1000. And then my final potential is going to be minus 1000. And I'm going to simulate it. And I get this. I am oxidizing here. And then it's perfectly reversible. Now, what if it's less reversible? So what I can do is I can change the reversibility by changing this heterogeneous rate constant. So if I change the heterogeneous rate constant, that's one way to create irreversibility. And what you would see is you'd start to see this peak separation, this peak splitting. And if I increase this by an extra order of magnitude, you'll see that as we become less and less reversible, this is the observation of how it changes. Okay. So, and then what happens to the graph if the concentration, let's go, if A is 10 times greater than that of B? Well, right now, I've simulated it in such a way. So, oh, there's one more thing. Let me go back to this fully reversible system. I can change it to just be irreversible, completely irreversible. And when I do that, you only get this. And if I zoom out, you'll notice there's nothing that'll show up on the reverse side. So it starts at minus 1 volt. It scans. It's the same current, same magnitude of current, 200, but there's nothing on the return wave. So I can zoom in. Nothing on the return wave. So that's simulate. That's when it's just purely irreversible. If I go back here, simulate, still get this high 200 microamps, and then it goes back to minus less than 200 microamps on the reduction. Now, right now, this is a situation where I only have A, but I can mess around with this when I have 10 times the amount of A as B. Now, in this case, I need to have some B in the system for this to work. So if I simulate this, this is what I get. It turns out that if this is a reversible reaction, some of the B is actually going to be reducing, going back here. So actually, the current actually starts here and it goes this way first. So all of this B is getting reduced. And you'll also, this is the current voltage profile, but you'll also see in the concentration profile, these start to get switched. So so A is red and it's full, but actually B, you can't actually see it. I may have to double check that, or maybe if I zoom in close enough. But it's interesting that B does not show at time equals 0. It does not show that there is 1 millimolar of B. It should show, unless this did not capture that information. But in this case, it does show. Let's see if I go to concentration profile and I simulate. Well, the concentration profile is a function of distance from the voltammogram is another different thing as well, because this changes dynamically. If I play this, you'll see the concentration profile start to change as a function of time. And similarly, you'll see the surface concentration change. So actually, when we start this initially, and I will stop this, I'll go to the beginning, and then start. Yeah, this doesn't, I don't know why this doesn't show 1 millimolar of B. It should start here. That's weird. Now, if I simulate, that's what we get. If I start to change things like the level of reversibility, let's look at what happens when this occurs. Well, actually, this still remains the same, but this process is what ends up changing as I become less and less reversible. So hopefully, this kind of answers your question, but I'm going to type this in the chat. The software that I'm using is called Aftermath Live, and it's a great platform for learning and understanding electrochemistry, playing with simulation software to actually learn how these things work. So there's several versions of this software. If I were you, I would just get the basic edition for 1 month. It costs $35, and you'll be able to play with it and actually learn like what actually happens when you have reversible and irreversible reactions, and what happens when you change the concentration of these two species. So it's a very powerful software, and I'd recommend it. Really, like I have actually learned more electrochemistry from using it. All right, I also put a link to Aftermath Live in the description if you want to check it out. Let me look at the next set of questions. Let's see. So BGMI Shorts asks, if I want to develop an, I think that's electrical double layer EDCL, should we avoid, let's see. I think EDCL, I think, I don't know if it's supposed to be DL, like double layer capacitor. Maybe I have this wrong. Let me see. So EDCL, oops, EDCL. Let me look. EDCL. EDCL in chemistry is a molecule. I don't know if that's exactly what you mean. I think what you're talking about is the electrical. Let's see. Oh, I'm getting this wrong. So there's electrical double layer capacitors, which is EDLC. Let me know if that's what you want, if that's actually what you're interested in, if you're trying to develop like an electrical double layer capacitor. Let me know if that's actually what you want. If that is what you're interested in, BGMI, yes. Okay. All right. I have confirmation. All right. Good. Okay. So yes, electrical double layer capacitor. So if I go back to this question, if I want to develop one of these, should we avoid the non-faradaic region? So the non-faradaic region is, in most cases, the electrical double layer capacitance. So I don't know if that's something that you want to avoid. Whenever you have any conductive material in an electrolyte solution with positive and negative anions and cations just floating around, you're always going to form some kind of double layer structure. Like you're always going to form some kind of capacitor in some way. So the non-faradaic region actually is the capacitance, because a capacitor is two parallel plates oppositely charged with a dielectric in between, such that no charge passes between the two plates. So faradaic reactions, by definition, require charge to pass through. Non-faradaic is when charge doesn't pass through and you have a capacitor. So you actually do want to, to develop an electrical double layer capacitor. You actually do want to develop the non-faradaic region. You don't want faradaic processes to occur. I have heard of things like pseudocapacitance that involve a level of faradaic processes, but it's something that I do not understand. But my limited understanding of it is that you can have some faradaic processes occurring in a capacitor that leads to increased energy. But I have to learn more about it because that's pseudocapacitance. So that's something that I need to learn or understand a bit more about. But I hope that answers your question, and I will, if you need further clarification, I'll try to provide you with more. Bill is asking, after I drink some water. Bill says, I got a little amount of silver when running CA stability measurements for long period, carbon-based HER catalyst. I'm suspecting it came from the silver chloride 3 molar KCl reference electrode. Is it possible? The electrolyte is 1 molar KOH. Oh, okay. Yes. Okay. So that is definitely possible. because silver is the only thing in your, because silver, at least in your experiment, sounds like it's coming from the silver chloride. And so I think that is absolutely possible. Silver chloride reference electrodes are typically not very stable in 1 molar KOH. Not because of the silver, but because 1 molar KOH is really at the cusp of, it's alkaline, so it can etch glass. If you had a dilute alkaline solution, you might be able to get away with some of these experiments. But as you move to like 1 molar and even higher concentrations, you'll start to etch away the glass. And yeah, I think I would say this just sounds like a contamination issue. But because you have these different electrolytes and the KOH is in some way reacting, I do believe that you may be getting some silver when running a long chronoamperometry experiment. That doesn't surprise me. One thing that you can do, Bill, is use a salt bridge. So if so let me at least just show you what it is. So Bill, there is let me show you this. Let me go to our website quickly. Chrome tab. Here we go. So let me share this. Hopefully you can see it. Let me double check. Oops. Let me double check. So yeah. So let me minimize your question. So this is a salt bridge kit, and basically you have your electrochemical cell. It's in green. It's the green cell, and then you have this long. Your reference electrode is this guy, and the reference electrode is put into a tube. Basically, it's a graduated cylinder that has a barbed fitting at the end, and then you have a huge like Tygon tubing all the way to another glass tube, and because you're working in KOH, you may choose a different thing, not glass. And then this goes into your cell, and there's actually like a frit, not all that different from the reference electrode frit. This is a way of separating the reference electrode from the electrochemical cell if you're doing something in a different type of electrolyte or you're worried about contamination. I have observed things like if you want to heat a solution, but you don't want to heat the reference electrode, this is a really, really great way or a great tool of doing it. So this is, if you just type in Pine Research Salt Bridge Kit, you will see this. And this is one way you can minimize the amount of silver, possible silver contamination, because the silver has got to travel all the way through the reference electrode, all the way through this frit, through this tube, and then through a frit into your solution. So when you're doing HER catalysis, this is a way of kind of removing it or not having it. So I hope that's helpful, Bill. Again, let me know if you have any questions about that. All right, all very good questions we're getting. Okay, so so Carlos is asking, hello, could you please explain what is the counter electrode used for, or why is it needed in a 3-electrode electrochemical cell? That's a great question. This is a hopefully a very simple answer. So the counter electrode, the purpose of it is to provide a counter charge or counter current to what's happening on your working electrode. So charge must always be balanced in any kind of electrochemistry experiment. So if you're doing an oxidation reaction on the working electrode, then a reduction reaction has to occur on the counter electrode. And that's what the counter electrode is just used for. It just maintains charge balance. Most of the time, we don't care very much about the reactions that occur on the counter electrode. But it depends on the type of experiment that you're doing. But for basic analytical experiments, again, you have a 3-electrode electrochemical cell. Maybe you're not doing electrosynthesis, where you have to generate macroscopic quantities of things. You don't care about what's happening on the counter electrode. But the counter electrode, the current at the counter electrode, the total amount of charge on the counter electrodes, is equal and opposite to that of the working electrode. But the potential required to drive that charge can be different. So counter electrodes are typically very large, much larger than the working electrode. and they have a larger surface area, and they also tend to be inert, which is a weird word, but active. They can easily undergo an oxidation or reduction reaction, whatever reaction is needed to drive your working electrode reaction. And so platinum is commonly used because platinum is very active. It doesn't take a lot of energy for platinum to generate an oxidation or a reduction current. So if you are, and this can happen, if you don't have an adequate counter electrode, your working electrode reaction is not going to occur. Not because the working electrode is bad, but because the counter electrode is either too small or not, or it can't actually react or generate the current that needs to be equal and opposite to that of the working electrode, or the charge that needs to be equal and opposite to the working electrode. So that is what the counter electrode is used for. And Carlos, let me know if you need any further explanation on counter electrodes. But that is why we use a counter electrode. In fact, a 2-electrode setup typically is just working in counter. Doesn't even have a reference electrode. Okay, so getting some good questions, seeing if there's any follow-ups. So, all right, let's see. So we have a question from Adiba Joshua. Can you elaborate on how to interpret OCP and LSV plot, especially for stainless steel corroding in HCl with inhibitor and without inhibitor? Let's see, how to interpret an OCP and LSV plot. So one thing that people do for studying corrosion of things like stainless steel is actually, they don't use LSV or OCP. They use kind of a combination, actually, of LSV and OCP. They do something called linear polarization resistance. And linear polarization resistance is it's actually a technique I need to know more about. But in short, linear polarization resistance, you measure the OCP, you have a stable open circuit potential, and then you sweep the potential very, very slowly. You sweep it extremely slowly to induce oxidation and reduction of your corroding steel. And usually you do multiple cycles of this kind of, like, you look at the OCP, do a little bit of this very small CV. It's like plus minus 10 millivolts that go at maybe 0.1 millivolt per second. So it's a very slow scan. And then the LPR, that's like one LPR cycle or iteration. And you just do a few of these with no inhibitor. And then when you add the inhibitor, because you're measuring the resistance, you see a resistance value that starts to skyrocket, where the current versus the potential, you have much, much less current and way more for the same amount of potential. So instead of OCP and LSV, you're really looking at this linear polarization resistance, and you need to put in some information like the density and the like the Tafel slopes. You need some of that information. Actually, let me see if I have. I can show you what the technique kind of looks like in general. So if you go to experiments, and let me just make sure that my screen is showing this. We have corrosion methods, and then we have LPR, linear polarization resistance. And so keeping track of the, I'm just putting in some of the autofill automated parameters that people mostly use. And, you need to determine the OCP. The OCP just kind of helps you figure out what's, with the other electrodes in your cell, your reference electrode, what is the open circuit potential. And then you're scanning the LPR waveform is actually a very slow LSV. But then you usually need some of these other corrosion parameters, and I hope that this is visible. It's not very visible. Let me hide this. So these other corrosion parameters that are a little bit hard to see, the corrosion rate parameters, sample area, the anodic and cathodic beta constant, equivalent weight density. These are all things that people use when doing LPR. And they'll do numerous LPRs it'll calculate a resistance. So you're looking almost at like a diagonal line. And that diagonal line at such a slow scan rate, and with some of this information, gives you a linear polarization resistance. And the diagonal line also is for, they have current on the x-axis and I think potential on the y-axis. So really the slope is the resistance. So I don't know if I can help you too much more than that, but hopefully I would recommend looking into LPR, linear polarization resistance. Do some research on LPR, and that will help you with actually interpreting the OCP and the LSV data to look for corrosion in stainless steel with and without corrosion inhibitors. Okay, so moving on. Kismat is asking, hello, can you please tell me if I am doing an organic catalysis cycle, and at the end of the cycle, if I need to change the oxidation state of the metal, then what should be my technique to do that? So, all right, so he's asking, can you please tell me if I'm doing an organic catalysis cycle, and at the end of the cycle, let's see, if I need to change the oxidation state of my metal, then what? Okay. So, the oxidation state of your metal. I need to know a little bit more, like, are you talking about homogeneous electrocatalysis, where you have a transition metal complex in your solution that's doing the catalysis, and you're oxidizing or reducing it? So usually for a catalytic cycle, you start with maybe, I don't want to say neutral, but let's say you're catalyzing iron or something. So iron may be in the +3 oxidation state. The catalysis happens at the +2 oxidation state. So you would need to reduce the iron to +2, and then that iron +2 does its organic catalytic cycle. It does its reaction, and then maybe if it's a 2-electron transfer, and so when the iron 2+ donates its electron, it becomes iron 3+ again. But then maybe you need a second electron, so the iron 3+ gets reduced again to iron 2+, and then does another step. So you're doing additional reduction reactions. So by doing techniques either bulk electrolysis or cyclic voltammetry, you are able to adjust the oxidation state of your homogeneous inorganic complex such that it can do the organic catalytic cycle. But without knowing, I might do CV without any catalyst, or I would say with the catalyst but without the substrate, not the thing that it's catalyzing. I would do some cyclic voltammograms of that first before I move to doing something like holding the potential to do an electrocatalysis reaction. This is for homogeneous electrocatalysts. Certainly, if you have a heterogeneous catalyst, you are changing the oxidation state, but how those work is a little more elusive, I would say. But hopefully that kind of helps your answer, or answer your question. Oh wait, before I get into that, he says, yes, that's a transition metal catalysis. Yes, okay. In that case, I would do, so now that I know that that's what you're doing, can you please tell me if I'm doing an organic catalytic cycle? At the end of the cycle, I need to change oxidation states of the metal. So usually the metals that are involved, or the transition metals that are involved, and of course I still need to learn more about this. Let me delete all this stuff here. So typically, let's say you have your metal. Let's say it's iron, and it's got some ligands. It's got ligands, and they're here. Okay, so it has its ligands, and it's in maybe the +3 oxidation state. And then when it reacts with, I'm just going to say, maybe it does some great CH activation, whatever thing. And then this becomes Fe or actually no. So let me do this. So first, before this happens, let me erase this. So let me erase this. So before this happens, why is this looking as if it's one whole item? Okay. So you have this reaction, and let's say this guy. Let me just copy him so that we have exactly the same thing on both sides. Except this part here, this guy is 2 plus. So let me get this back, and it's going to be 2 plus. So you used electrochemistry to give this guy an electron, and then it's 2 plus. This guy then reacts with some molecule. Let's just make it cyclohexane or something like that. And then it converts back to Fe3 plus. So that's what's happening. So the technique that you want to use, like if you know this is the reaction, you just need to apply a negative potential. So the technique that you might use is bulk electrolysis. Bulk electrolysis. Sometimes chronoamperometry it basically does the same thing. But if you want to study these reactions, you might do cyclic voltammetry, where you can see the reduction or oxidation. And when you do CV of these types of systems, this is the CV without. And let me make sure that I'm not blocking. Yeah, I'm actually blocking what you said. This little CV down here in the corner. This little CV is just without the substrate, just a regular reduction or oxidation reaction. But then with the catalyst, you end up getting something like this. It's not perfect, but where you have much higher current because this process is happening a lot, and usually this is getting consumed, so you don't have any of the oxidized or reduced species left to have the reverse reaction. If this is in fact, a reverse reaction. So hopefully that helps you with understanding, understanding the techniques that you can use for doing an organic electrochemistry cycle, or to change the oxidation state of your metal. Hopefully that, let's see. So actually he gives me some more information. Let me see. The counter electron, I'm expecting HER to occur. And should I use a 3-electrode setup or a 2-electrode setup? Yes, you're right. Of course, because everyone does CH activation. It's just, everyone loves to do CH activation. So, so I prefer using a 3-electrode setup. I like having a stable reference electrode to know at what potential something's happening at. It's not necessary. You can do electrocatalysis with a 2-electrode system. And yes, if you are doing this, if I'm assuming maybe you're doing some non-aqueous stuff possibly. So if you have hydrogen or maybe a little bit of acid, that can be used as a sacrificial reagent, so that hydrogen is the only thing that gets generated at the counter electrode. So hopefully, but yeah, I would say do some CV initially, and then do bulk electrolysis, applying either a strong negative potential or a strong positive potential around the potential where the oxidation or reduction peaks show up in the CV. And that is the potential where this reaction just happens very quickly. So hopefully that is helpful. And I can talk a little bit more about this later once I get through some other questions. So I do want to get through some of the other questions that are coming in. But this is very good. This is great questions from everybody. Garley has a few questions. I'm going to try to go through them. So Gargi says, "Hello, sir. Can diffusion controlled process be a non-faradaic process? The surface morphology of my electrodes is multi-layered graphene sheets, and its CV is a perfect quasi-rectangular curve." Wow. Okay. I just want to read what else. And when I calculated its current contribution using trassati approach, which I don't know what the trassati approach is, I found that it has 93% diffusion controlled and only 7% surface controlled. The measurements were done using a three-electrode setup, 1 molar KOH. My question is it possible to have diffusion of K plus and OH minus ions into the multi-layered structure? Okay, so let me think back. So he has multiple graphene sheets. And in general, can the diffusion control process be non-faradaic? So let me think about that for 1 minute. It's a good question. Let me talk a little bit about my thought process, for example. So diffusion is the random motion of molecules. It's just it's a mass transport. It's a way of stuff getting from point A to point B. Diffusion is the random motion of molecules. It's just molecules just bumping into each other randomly. It's a random walk. For a molecule, in some cases, for a molecule to get from point A to point B, it has to be through this random motion. It's not through convection. It's not through migration, which is the movement of molecules in association with an external electric field. Things like double-layer charging are described at least as not diffusion controlled. And so can you have non-faradaic processes that are diffusion controlled? So there's a part of me that wants to say, yes, you can. A Faradaic process just means that there's an electron transfer. You can have molecules moving around randomly, and they can generate, them getting to the surface, them getting through your multi-layered graphene sheets, I believe is diffusion controlled, because you are describing OH minus and K plus ions, the ability to. So the only way those guys are moving, in principle, is through diffusion, which may be the reason why you're seeing, or why you're getting, this diffusion controlled current through your multilayer. I think that that's possible. I think 1 molar KOH having K plus and OH ions, because it's not like it's diffusing through solution and getting oxidized or reduced in this case. It's just being able to move through the structure. And this is a very interesting. I might actually recommend you look at a guy. His name is Yogesh at MIT. Let me see if I can't find this stuff. I know some of his work. Chemistry. Actually, he just goes by Yogi, but I'm pretty sure his name is Yogesh. Yeah, Yogesh Saranda. And he has one of the questions, some questions. I listened to a talk of his, and he was describing, like, well, how do you measure, like, what happens if you have, like, a perfect conductor, and then you have something that's semiconducting, or not semiconducting, but you have conducting layers on top of it. Can you measure how electrons transfer through those different layers? And he was able to build some interesting things. And it sounds like what you have is you have something that's very conducting, and then you have graphene sheets on top of it. You have some multi-layer. And you're thinking about the movement of the potassium and the hydroxide ions through your multi-layer. And I believe diffusion is the only mode of mass transport that's going to allow them to move through it. I think graphene is a very interesting species, and I don't know enough about its electrochemical properties. Does that give you some level of mass of mass transfer as well, like, or electron transfer as well. So I think you might be onto something with the diffusion of K plus and OH minus on the surface. I don't know what kinds of potentials you have to apply to get, like, I don't know what your current response looks like and for what technique. Or actually, you're saying, oh, right. So you're getting, okay, the CV is a perfect quasi-rectangular curve. So, I have to think about it a little bit more. One thing that, so one thing to keep in mind is the rectangular curve is usually for some level of double layer charging. You can do a scan rate study of, so actually, well, here we go. So Gargi, one thing that you can do is you can do a scan rate study of this. I'm curious about what the scan rate study is. So if it's a capacitor, if the capacitance should have a linear relationship. So the current response that you get for a perfect rectangle, quasi-perfect rectangle, that increase in current should be directly proportional to the scan rate of your system, because the current is equal to the capacitance times the scan rate. I would be interested in seeing whether or not you have a linear dependence on the current for your diffusion, for your CV with this quasi-reversible thing. I suspect that because you'll have a direct 1 over T relationship. Typically, diffusion controlled processes in electrochemistry, they have a 1 over the square root of T dependence. So let me just write that down so that we can all kind of so you know what I'm talking about. All right, so let me delete all this inorganic chemistry here. So for a voltammogram that's kind of like this, sort of say it's double layer capacitance type of thing. The current, so this is voltage, this is current. The current is equal to the capacitance times the scan rate, dV dt. This, I have always looked at, this is a 1 over T relationship. Diffusion controlled processes, diffusion, have a 1 over the square root of T dependence. The current is proportional to 1 over the square root of T dependence. This is easy, T. So I am curious, this is a curiosity thing, is whether or not if you do a scan rate study and you have multiple ones of these kind of going up and down, or sorry, up and here and all that. If you have multiple of these, is the current that you measure 1 over T or 1 over the square root of T? That is my question to you, because that may also give you some indication about the nature of diffusion control. That's just a thought for this. They have a very interesting system. I tend to lean towards diffusion, but I don't know. Okay. FCB, just going down the list, I will get to, I know Fred has a question, and I'll try to answer it, but FCB asks, how to choose the scan rate of CV if the scan rate changes the position of the peak? Oh, if my CV curve is not smooth, what is the meaning of this? All right, so hold on one second. Okay, so most people will choose a scan rate of, say, 100 millivolts per second. That's the standard like starting scan rate for most of these things. So and then you might go faster, or you might go slower. It depends on what you're looking for. But if the scan rate is changing the position of your peak, you most likely have either a kinetic issue, but most likely you have a uncompensated solution resistance issue. The peak position should not, in principle, should not change as a function of scan rate. Of course, if you have slow kinetics, it's going to change. But if you have but if it's supposed to have fast kinetics, you may have uncompensated solution resistance. So, I think that you probably need to look to see if you have any uncompensated solution resistance. Now, if the curve is not smooth, what does that mean? If you have some noise, my guess is if it's not smooth, you have sharp peaks somewhere, which I believe might be noise. It can be electrical noise. I'd have to actually see the noise and where it is to get a better idea. There are smoothing features in a potentiostat, either via filters or post experiment filtering that can be done to kind of remove any jagged edges. But you could be sampling very, very quickly. That can lead to noise. Something could be vibrating in your system, right? You're trying to minimize mass transport convection. Stirring the solution can cause noise. And also your electrode, like if your glassy carbon electrode's dirty, that can also cause noise and spikes and stuff like that. So there's a variety of things that could be the reason why your CV is not smooth. So FCB, I hope this is helpful. Let me know if you have any questions about that. Okay, so Fred is asking a question that I may or may not be able to answer. I looked a little bit ahead, but how to get a Mott-Schottky plot if my potentiostat doesn't have the mode for it? Can I just measure EIS with constant frequency and scan the potential? I get the, I think that's supposed to be the CS values from the CSV file for this. So CS, I'm assuming it's the space charge capacitance. And just looking because Fred, okay, so how to determine the appropriate potential range, and then how to determine the appropriate potential range for Mott-Schottky. So, so I believe you can. I do believe that you can do EIS. I wouldn't measure it at a constant frequency. I would measure it at a series of frequencies. And even if you look at some of the literature on semiconductor electrodes, you will find that there are several frequencies. You actually get different space charge capacitances and different values at different frequencies. I don't know. There's speculation about what that means. But you do want to do EIS at a variety of frequencies, a small range, not a lot, at a specific potential. And then, yeah, you want to calculate you actually want to do maybe a circuit fit. And there are numerous types of circuit fits for Mott-Schottky depending on your system. So there can even be, I remember seeing one from Bard. Let me see if I can find it. Give me a second. So, give me a second to see if I can't find. Yeah, there are several. I'm gonna open up a few publications. I remember there was one. Remember there was one from Alan Bard where he actually showed the. No, that's not the one. Keep it. Predation. For some reason, I have some annual reports here. I'm trying to see if I can just find like a circuit model, because sometimes the circuit model is not what you think it is. I'm surprised. Or it may even be. Yeah, there was a publication where they actually showed the circuit model that they used for Mott-Schottky, and I had one of those, and now I can't seem to find it because I don't have a lot of publications to my name. But either way, you do want to think about what the circuit model is, and then try to fit it to that. So that's the. So I'm sorry I can't tell you what that circuit is, but then yes, you can get the space charge capacitance values from it, and then regarding the potential range, I don't know enough about the selection of the potential range. I think it's going to depend on what your semiconductor material is. There is, and actually this is a paper that I think I do have. So if I share my screen, I share, where, let's see, here we go. So hopefully you can see this. But depending on these are the energy band positions for some oxide semiconductors. This is on a vacuum scale, of course, with electron volts. But this is gonna, in a way, tell you, oh, I need, like, if you have copper oxide, you might actually have a pretty narrow range. Each one of these is like a volt. Like an electron volt is a volt. And then you have to figure out like roughly what your reference electrode position is. This is actually energies for the reversible hydrogen electrode. So, oh no. So yes, these are the redox pairs for, say, hydrogen evolution and then oxygen evolution. So this paper in particular, this is ChemPhys Chem. Actually, I did not check to see whether or not people can see this or not. Yes, it has a space charge capacitance, and then. Oh yeah, I'm looking at what Fred's asking next. I also wanted to ask how to determine the circuit model if I have a standard 3-electrode system with a thin film working electrodes. Okay, so first I do think that that for this is going to give you a better idea about what your potential window is. Also, if you have doped your metal oxide or your semiconductor material, this whole thing, like the Fermi level, shifts around a bit. So you want to be a little bit careful. I would do stuff around the open circuit potential. So the open circuit, to my knowledge, the open circuit potential of a semiconductor material is, because you'll have like a reference electrode connected to this. The open circuit potential is the Fermi level of the semiconductor. So if I stop sharing, and this is of course my extremely limited knowledge of semiconductor electrodes. So again, very, very limited knowledge of semiconductor electrodes. I'm trying to learn more about Mott-Schottky and how they work. But generally speaking, you have a conduction band, you have a valence band, and then you have your Fermi level in between. So this is valence band, conduction band. This is at some kind of interface. And most people actually draw this as like one continuous thing. And then this Fermi level is here. The Fermi level will move up or down if it's N or P doped. So if it's N doped, it goes up. If it's P doped, it goes down. But the OCP that you measure, OCP, should be a measurement of where the Fermi level is. And of course, this whole thing is on an energy scale. I'm sorry I'm doing this backwards. I didn't think this completely through. Everyone draws it this way. So once you're at the Fermi level in the OCP, you can start to move the potential back and forth a little bit to kind of move these things around. But I would be careful because whatever your electrolyte system is, that has your Fermi level is actually going to be pegged. I forgot. Your Fermi level is pegged at the redox potential of your system, and at that point, your bands have already bent in some direction. I don't know. I don't understand enough about how band bending works. Or what even really is band bending. So you may already be in a banded position, and so the potential range, I think, should be just a little bit in and out of the OCP around the Fermi level. But sometimes if the Fermi level's up here, if you go too far in one direction, you'll actually go into this this kind of weird cross zone where the majority carrier or the minority carrier inverts itself or something like that. So, Fred, this is all to say that I really have no idea. But those are the things that I think you have to think about or look at. And you want to determine a little bit more of the circuit model for a standard 3-electrode system. So the circuit model of a thin film for this, it's a little complicated. I've seen a few. I just don't know where. There was a paper that like Bard had on this, and I'm really trying to like understand, where did it come from? Like I could have swore there was a paper from Bard where he talked about semiconductors, and oh, that's not it. And I cannot figure out what circuit model they used because your surface, mainly the important thing is that they kind of had this, there's the space charge capacitance, there's the capacitance of the electrical double layer, and those are in series with one another. And then there's these separate, there's a separate resistor. There's charge transfer resistance. There's also resistance associated with certain surface sites. So your semiconductor can have surface sites. And I have seen, I'll draw something very, very quick that I don't know if it's really good. But I've seen circuits that look kind of like similar to this, where it's like it goes three ways. So there's like this resistor here. There's like a capacitor here. Maybe there's a resistor here. And then maybe there's another, I don't know if there's another resistor here that, there's kind of like two, and actually this one may have a resistor, sorry. But I've seen some that have like three, these three parallel paths, sort of say, and that there are these two capacitors, space charge and double layer capacitance, in series with one another. But I've seen that this is like surface site reactions, and this is just like your redox reaction, right? There's a redox reaction occurring. You'll have a Randles element associated with the redox thing that pegs your semiconductor to the surface, or not to the surface, but pegs the Fermi level of your system. So they're complicated. They look a little bit like that, but this is something that I would recommend looking up. I'm sorry, Fred. I wish I could give you more information. Okay, how are we doing? All right, moving on. Jeffrey Josephs. He's asking, hello, I use metal selenides. The activation of the material takes more than 2,000 cycles. That is, I'm getting higher current only after 2,000 cycles. What could be the reason? So the nature of activation usually has to do with, in a way, something is on the surface that's not allowing reactivity to your metal selenide. And it's only after 2,000 cycles that you're able to kind of remove that thing that's unactivated. I'd be curious to know whether or not you have a way of cleaning the metal selenide, like polishing it, removing stuff that could be on the surface. Something is on the surface that's very difficult to get off, is what it seems like. Only after 2,000 cycles. One thing you may want to try is going to a higher negative or a higher positive potential when you're doing these cycles. That might be able to decrease the number of cycles, because when you move the potential window of your cycling to slightly more, you're hitting your electrode with a more positive potential or more negative potential to kind of get rid of those extra things. So that may be another reason why you have so many cycles that's required to activate your metal selenide. So hopefully, Jeffrey, that kind of helps answer or address your question. Let's see. Fred says, thanks for the explanation. All right, so Arjit, nickel foam coated with a metal oxide, and metal oxide is the active material for a supercapacitor. Will there also be a Randles element between the metal oxide and the nanofoam interface? That's a great question. So I would say I think the answer is yes. I think the answer would be yes. And the reason why I say that is usually whenever there's an interface, and again, it depends on how the interface works. So if the metal oxide is producing enough of a insulator between the nickel foam and the nickel oxide, then you can have capacitance. But it can also just be a resistor, because you could have a layer of nickel atoms and then just a layer of like nickel oxygen atoms, and all you're dealing with is electron transfer between them. So only if there's a sufficient thickness of this nickel oxide, and there is no, like, you need some kind of capacitor, charge separation for there to be a Randles element. Because otherwise, then it's just resistance, and like there's just charge transfer between nickel of two different oxidation states. Metal, nickel, and then nickel oxide. They have two different oxidation states. You can have electron transfer between those two. So in a way, it may be the case that another thing that would help is if you saw the impedance data as well. In the Nyquist plot, do you get, say, another semicircle, or does it manifest itself as just a resistor? There's very little capacitance, sort of say. So that's my thought. That's my thought about whether or not you would have another Randles element. Generally speaking, a lot of people do. I think it depends on the degree of the capacitance and the nature of it. You may even have some inductive loops in it as well, possibly. Which I don't know if that's true. All right. Okay, let's see. So Sumaya is asking, what happens at the counter electrode during electrolysis at working electrode doing ORR? Also, is it always the same and opposite potential being applied at the counter with respect to the working? Please discuss. That's a great question. So it depends on your system for ORR. So the oxygen reduction reaction at the working electrode necessarily has to be reducing something. So it must be reducing something. So some oxidation reaction has to be occurring at the counter electrode. And depending on what your electrolyte is, it's going to depend on what the platinum counter electrode, say, is doing. So if you're oxidizing something in water, usually you're generating oxygen. So most likely it's the case that you're, I believe you're probably oxidizing water to oxygen, which is the opposite of ORR. You're trying to reduce oxygen to water. So that is my guess as to what would be happening at the counter electrode. Of course, if there are other materials, some people add sacrificial agents, so you could be oxidizing something else if there was no water. But usually, I would say if you just have water as your electrolyte, or if you have OH minus in some way, you could be oxidizing hydroxide groups or something like that. And then now, is it always the same and opposite potential being applied to the working electrode, to the counter electrode with respect to the working electrode? So counter with respect to working is going to be the same in the sense that if I measure the potential difference between the counter and the working electrode, and then I flip it for working with respect to counter, they'll be equal and opposite. However, with respect to the reference electrode, you'll have a very different value. So you may apply plus 1 volt, or in this case, you're doing RR, minus 1 volt to the working electrode with respect to the counter, with respect to the reference electrode. But the counter electrode might be something like plus 3 or plus 4 volts with respect to the reference electrode. So it'll be opposite, but it'll be very different. It will be enough voltage to provide an equal and opposite current or charge from the counter and the working electrode. So that is what would happen. So there is this difference in potential, sort of to say, between counter and working, and that's with respect to that's kind of with respect to the counter electrode. So I think that Samya, I hope I'm pronouncing this correct. I hope that answers your question. With respect to the reference electrode, you'll have different voltages. The voltages will not be equal and opposite. And the other thing to mention is that if the voltage between the counter and the working electrode gets too high, even if the voltage between the reference and the working is relatively low, you'll run into a compliance voltage issue, which is the limit of how much power your amplifier can provide. So hopefully that answers your question. Please let me know if you have any question, if you need any further clarification. Okay. So bye. I will get to your question. I'm just going in these in order. So first off, Chris, good to see you. It technically isn't Friday, but Neil and I will be out on Friday. So our summer schedule is just very, very crazy. Almost every other week I'm traveling, and then most of August I'll be out. So I'm trying to do this now, at least on a Thursday. Maybe get some new people who can't normally visit. So hopefully, so this is not probably going to be a regular thing. But yeah, I wish it was Friday already. Fred is asking, do you need to purge the electrolyte with argon to eliminate O2 for EIS? I don't think so. So with EIS, one thing that's important is you're only applying a small perturbation. Your sine wave is usually pretty small for potentiostatic EIS. So you might not even be applying the sine wave in a region where oxygen is going to get in the way of your signal. But you don't need to use argon. You don't even have to really, you can use nitrogen too. That also works if you're worried about oxygen. But I don't know if oxygen will manifest itself in the EIS. It will only manifest itself if your EIS baseline is at a potential sufficiently negative to reduce the oxygen, because then you have perhaps another semicircle associated with the reaction with oxygen. So hopefully that answers your question. But you don't need to use argon. I would still keep the system very, like, I would degas if you want to degas it, and then I turn it off and keep it as steady, and then make sure nothing else enters the system, because you want your EIS to be stable. But Fred, if you're doing Mott-Schottky, most of the time you're not even going to be going to a very low frequency when collecting data. You actually are mostly within a fairly high frequency region. Maybe you're going as low as, I don't know, 1,000 hertz is as low as needed. But anyway, I digress. Hopefully that's helpful, Fred. Ananda Patel, what can be the best way to prepare ni-foam-based coated porous carbon electrodes? I don't know. I don't know. I don't know anything really about preparations of a nickel foam coated porous electrode. So I don't know anything about how to prepare such a thing. Most people buy this stuff. They would buy nickel foam, or they'd buy carbon foam, but I don't, or porous carbon electrodes, but I don't know anything about the preparation of it. I might just do silicon voltammetry and dilute acid to activate the surface. That would probably be the only thing I could think of. But I don't know enough about the application, Ananda. Let's see. So we're getting... all right. Okay. So... All right. So Hello Bye is asking about a breakdown. What is breakdown voltage? What is breakdown voltage? I don't know what breakdown voltage is, but if I do a quick Google search, because maybe I can maybe it's just oh, okay. So breakdown voltage is described as the voltage. Basically, it's the minimum voltage required to cause a portion of the to basically become electrically conductive. So if you have an insulating material, something that doesn't normally conduct electricity, the breakdown voltage is the voltage required to basically make it conductive. And in a way, I would think of that as most materials have some kind of band gap to make them insulating, and the voltage that's required to overcome that band gap is the breakdown voltage, where you can now conduct electricity through it. You've supplied sufficient voltage to make your material go from being insulating and not conducting electricity to conducting electricity. Now, of course, usually when you apply a very large voltage to insulating materials, there's a chance that other things can happen, like fires or explosions. So I'd be very careful when doing any work associated with a breakdown voltage. If it's anything, if you're looking at something and it gives you a breakdown voltage as a specification, that means you should probably stay away from that voltage when using it. Okay, so let's see. Okay, so and I'll get to other people's questions. I know Fred mentioned something else, but Arjit is asking, when we represent a Randles element, we consider a RC parallel circuit at the electrode solution interface and RU for uncompensated solution resistance. But why don't we take another RC parallel circuit for reference electrode solution interface? Oh, that's a great question. That's a good question. So for the reference solution interface. Yeah, so let me at least draw what you're talking about. So right now the working electrode, and I'll have to probably stop this live stream relatively soon. So the working electrode has been typically modeled this way. You have your Randles, a Randles element. Then you have your uncompensated solution resistance, and then this just goes to ref. Right. All right, so this is like your uncompensated resistance. This is your double layer capacitance, and this is your sometimes charge transfer resistance. And what you're asking is, well, why, the reference electrode isn't just this. Why isn't there a why isn't there a double layer capacitance and a charge transfer resistance for your reference electrode? Right? Like, why doesn't this exist? Or why isn't there something else here? So the reason why we don't have that is because, well, well, actually, I'll spoil this a little bit. A reference electrode actually it actually does have a little bit of this. If you actually look at a reference electrode construction, it actually has it has some elements of it. So you have this frit. This is how reference electrodes, like how I would think about them from a circuit model perspective. So this here is a resistor. This is the frit. So the frit is a resistor. But there's actually a capacitor, which is, I'll just kind of draw it like this, sideways. There's a capacitor here. This is the glass. At the high frequencies, you actually can run into high frequency noise in your Nyquist plot because of the glass impedance. There's like 8 picofarads of capacitance because there's a charged surface on the outside of glass. There's charge on the inside from your KCl solution or something. And the thickness of the glass is it's an insulator. It's a dielectric. And you end up getting 8 picofarads of capacitance. So yes, realistically, actually, you kind of do have this. You're right. You actually do have this reference electrode. But what we the thing that's interesting to think about with impedance is impedance fundamentally. And let me. I'm going to minimize your question so that I can have a little more space to write. But impedance, at the end of the day, let's see, V equals I R. So I always want to get this right. Voltage over current. Here we go. Voltage over current. So impedance is fundamentally this. It's the voltage over the current. We measure a voltage, we measure a current. But what exactly is that? So the current, there's actually current associated with the sorry. There's current associated with the counter electrode. That's what I want to say. The counter electrode. There's actually current associated with the counter electrode. And the voltage is just measured between the reference and the working electrode. So all the voltage is measured between, between working and reference. So some of these elements, it actually, and the voltage is measured kind of at this tip. It's really at this tip right here that the voltage is measured. A small amount of current is necessarily required to make a measurement of the voltage, and it goes through the lowest impedance process, which tends to be this resistor. But that's what's done, and so this circuit element is not implied in EIS. This current also does have a contribution from your counter electrode. So you bring up a great point. The current has, in a way, your current has contributions from the counter electrode, which does have this Randles element. So, and let me make sure that I have not skipped any questions, because this is Arjit's question, right? So yeah, we don't have those, and the reason why is just because of the nature of how we measure the voltage and how we measure the current when we're doing it. So all these extra elements in your reference electrode and your counter electrode are not implied, and actually the counter electrode impedance, in a way, or the counter electrode contribution from the current is, in a way, contribute because the current is the same at the counter electrode, and its phase information is the same. So any phase delay at the working electrode, it's the same phase delay at the counter electrode. I have to double check that, but I'm pretty sure that's how it works. I would need to look that up. So maybe that's wrong, but I do think that the counter electrode does have to produce different phase. So hopefully that that answers your question, Arjit. So Fred was asking about general degassing. General degassing EIS. I think as long as the system is stable, that's, I think, one of the most important things. And then when if your system is changing, the validity of your EIS data becomes like lower and lower. So that's kind of that's what I worry about, sort of say. But yeah, if you are applying a negative bias, a strong negative bias around that sine wave, and you have a reaction associated with oxygen, that's the biggest problem with oxygen in electrochemistry, is it contributes to your signal, and you don't want it. That's why we degas. So hopefully, Fred, that answers your question. So GC Danny 271 asks, how does a binary divider work, the kind which you repeatedly subtract the denominator and count how many times you subtract it? I don't know. I don't actually know how this works. I actually don't know how this is used in electrochemistry as well. So I apologize. So yeah, no, I apologize for that. Yep, sorry, don't know the answer. Let's see. Someone else, thanks for the clarification. So basically, in between the working and counter, it's the current which needs to be the same, right? Potential doesn't need to be exactly the same and opposite magnitude of the counter. Correct. So the I think current is weird in the sense that you need to have like conductivity between the working and counter electrode. But yes, the current and hence the total charge on the working and counter electrode needs to be equal and opposite, but the potential required to reach those states of charge will be different. So yes, that's correct. Let's see. Can you utilize IR drop in a simple way? Can you utilize IR drop? Can you utilize IR drop in a simple way in GCD plot? I don't know. I don't know enough about because I think galvanostatic charge discharge plots they plot things correctly. You could try IR compensation, but it's weird because in GCD plots you're typically just applying a static voltage, or no, sorry, you're applying a static current and watching the voltage change, increase or decrease if you're charging or discharging. I don't know how IR compensation works in a galvanostatic experiment. So that's something that I would need to look up, Anand, to know a little bit more about it. But we do have a few more questions that it's like, oh, I had some questions previously prepared, but it looks like I have a lot of questions to answer. I might not be able to get to some of those. Let's see. So, Slitty Steven. Hi. For impedance spectroscopy, how does the phase shift between reference and working electrodes vary over frequencies? What does altering frequency change? Thanks. Let me see. So for impedance, how does the phase shift between reference and working electrodes? So, oh, okay. So, okay, I think I understand. I think I understand your question a little bit more. So, I talked a little bit about this for another question, but when we let me share the screen. So it's not so much the phase shift. I'm gonna make this a little bit clearer, but the reference electrode, when you use a reference electrode, there are two avenues for current to flow. There's a little bit of current that has to flow for a reference electrode to work. There's current directly through the frit, which is just a resistor. But then there is another mode, which is the capacitance here. There's capacitance of the glass. And when I learned this, I thought it was the absolute craziest thing. But there's about 8 picofarads of capacitance through the glass. And maybe there's like 1 kilo ohm of resistance through this frit. So in principle, there's almost no phase delay between the reference and the working electrode. And truly, the working and reference electrode, it's just a measurement of the current. It's a measurement of the voltage, what's applied and what's measured. But if the current passes through here at high frequency, so this is at high frequency, then you're going to see some errors, sort of say, some errors, because there's a phase delay when you have a capacitor. But at mid to low frequency, all the current is going through here because this impedance becomes almost negligible. Or no, it's not negligible. It becomes super high. This becomes really, really large. The impedance of this capacitor becomes very large as the frequency decreases. So all of the current at between this kind of reasonably-ish high, but really mid to low frequency goes through here. So this is like mid to low frequency. Goes here. And so there really isn't, because this is a resistor here, there is no phase delay. So I think that I hope that kind of answers your question. And then, and of course I will, let's see if there's any, no follow-up from Slidey Steven. But what does altering frequency change? And really altering frequency just changes the path of least resistance between the working and reference electrode when making a measurement of the voltage during EIS. So I hope that kind of answers your question. But let me know if you need further clarification or if you were asking for something totally different. So I'm gonna skip questions that have to do with adding and subtracting quotients. So I'm sorry, GC Danny 271. I don't know if that's has to do with electrochemistry. So I might skip that for now. All right. So Sama asks also, is this why we prefer to use small area working electrodes and relatively large counter electrodes for CV, which will minimize the voltage load at the counter electrode with respect to the working? So Sama, this is one reason. You are exactly correct. This is one reason why the counter electrode area is much larger than the working electrode area for 3-electrode systems. It is to make it so you can imagine if I have a very large area electrode, I don't have to apply as much of a voltage to drive current, to drive a reaction. It's like, I just need it's like the surface charge of my counter electrode. I just have to move it a little bit and I get lots and lots of charge to pass because I have a very large surface area. More current will pass. And I have, I've done this actually. This is an experiment you can do. If you switch the working and counter electrodes and you try to apply a super, super large voltage through a really, really small area new counter electrode to get a big, to get a lot of current out of your counter electrode, you will run into a compliance voltage issue. The voltage will just get way too high, and your experiment won't work. So that is correct. That's one reason why one of the main reasons we use small area working electrode and then large area counter electrode. And similarly, if you do use large area working electrodes, if you can increase the area of the counter electrode, that would help your experiments quite a bit. Let's see. Okay, let's see. So Arjit asked the question, maximum of published paper has reported that EIS should be done at OCP or 0 voltage with respect to reference electrode. What is the reason, and how do we measure the impedance at 0 volts? So, maximum of published papers report EIS should be done at 0 OCP or 0 voltage. I think it depends on what you're doing or what you're looking at. Most systems, you know, the change. So actually, I'm going to. I think it depends on what you're trying to do. Like if there's something happening in your system, and it happens at a very specific voltage, you should do EIS at that voltage as long as the system is stable. Otherwise, you're not going to see it. Like if you're looking at charge transfer resistance for a redox active molecule, if you just do it at OCP, you're not going to see anything. Like at OCP, the reaction's not happening. I assume it's not happening. So you need to apply a negative or a positive voltage to get your redox process to occur. And only once it's occurring, then you can start doing EIS. And actually, it's a it's kind of it's kind of a nice thing you can actually look at. So if you if I get rid of this for now, so if you're looking at EIS, so you have like your Z real, and you have a negative Z imaginary. So sometimes you get some Nyquist plots that look like this, and then they tailor off. You also get some that look like this, tailor off, and you get some that look like they're huge, and then they tailor off. And so this distance here, actually, let me make that red so it's a little easier to see. So this distance is charge transfer resistance, and this is at different voltages. This one here maybe at 0 volts. This one's at like say minus 0.5 volts, and then this one's at like minus 1 volt. And that's helpful to see. Like that's your RCT is changing as a function of the potential that you are applying and doing EIS at. So I think it's helpful to actually do EIS at different potentials as long as the system is stable. So it's going to depend on the system. I think it's really going to depend on the system. Now, how do we measure impedance at 0 volts? So all you would do, I'm just going to show you what it is in our software, but every software that you use, if I just do experiment and if I go to impedance spectroscopy, you can see that you'll have an area that should be like the EIS baseline. The EIS baseline is where you set that voltage, and it's versus reference or versus OCP. If it's versus OCP, you need to do OCP first. But if it's versus reference, like that's 0 volts versus the reference potential. So that should be a setting in your potentiostat, and then of course you can make changes to what's the amplitude, the AC amplitude that you're applying around 0 volts. So that's for our software, that's for our potentiostats. So of course I'd recommend using our potentiostats for some of these systems. I think I can take maybe one more question, but I don't know if I'm going to be able to answer it. This is from Gargi. So specific capacitance with respect to area is more significant, farads per square centimeter, or farads per, with respect to mass, specifically in case of a 2-electrode device measurement. I think maybe some same doubt for energy density and power density calculations. I don't know. I think it's going to depend on perhaps the density of your material. I think the density is going to be important, right? If it's based on mass and if something's very dense, then I think area may be more significant. This is just a guess. I really just think it's a guess. Because area is more, I don't know, indicative of capacitance. But if you're an engineer and you're trying to make something with you don't have a space constraint, you have a weight constraint, then mass is going to be more important. So I'm not so sure exactly. This is also something that I don't work on quite so much. But that's my opinion. And unfortunately, we're out of time. There were some questions I was hoping to get to earlier, but hopefully my colleague Neil for next time, because I will be running a workshop at the University of Texas Tech in Lubbock, Texas, next week. And so I won't be here. And tomorrow I'm helping with another workshop, a dry run for it, so I won't be in the office. And Neil is out. Actually, Neil's in Texas right now. So this concludes this episode of Ask Us Anything about electrochemistry. I think we had a lot of really great questions and some great engagement. And I think Neil and I are going to try our best to provide as much as we can and do as many of these as we can in the summer, given our schedule, because we are traveling a lot during the schedule. And so, this is on Thursday, but I think next time it'll be on Friday, and then the week after that maybe it'll be a different day. But thank you for staying tuned. Subscribe to the Pine Research YouTube channel and our Twitter account. We usually make announcements, especially on YouTube, if there's going to be any changes for an upcoming live stream. So once again, thank you so much for tuning in, and I'll see you soon.